This is the stress and strain lab, and here are the objectives, and here are some or all of the answers for the theory part, and here are some or all of the answers for the procedures. For example, if the knot slips, you would have to retie it. That you would have to measure the original width, thickness, and length only once. And then as you put more mass on, you would have to measure the length for each new mass. And then you enter all the data into Excel. And in Excel here would be the original data, and the way I have it posted here might be slightly different from what I have in the posted video. Then here are some example data, and these graph a little strange only because there are a few data, but you can see here if it wasn't for this strange curve here, they would kind of go nicely here, and you will see that in your own data as well. When you add new data, for example, I'm going to make up a few here. 331, for example, 339. Then all you have to do is grab this one here, pull it down, that little square, highlight all of these here, pull them down, and everything is graphed automatically. Again, my data are a little funky. And these were, of course, my example data. This is the hydrostatic pressure lab. And here are the objectives. And here are some or all of the answers for the theory part. And here are some or all of the answers for the procedures. So, for example, on the 2-liter soda pop bottle, make 5 marks for 8, 12, 16, 20 centimeters, and then as the water is running out, you measure the distance, which is the furthest part of the distance of the water stream for each depth of the fluid. However, before you even start, you measure the vertical drop height of the water, and you do that only once because that remains constant throughout. As you do the calculations, keep in mind that you're measuring in centimeters. You should use G equals 982 centimeters per second squared. These are my example data. They might be different from what I posted in the video. So here I used a very long tube instead, and so I had a water depth of 91.5 centimeters. Calculated this velocity with which it should come out, measured the horizontal distance, 70 centimeters, so a little over 2 feet, and calculated from that the actual speed with which it came out to 210 centimeters per second, and so the ratio of the two is 0.49. Again, in the video I might have different numbers. This is the specific heat capacity lab, and here are the objectives and a few statements in the theory part. And here are all or some statements for the procedures. For example, that you have to measure the mass of both the water as well as the specimen, that you have to measure the temperature of both the water and the specimen, which means either in the hot or and in the freezer, and then the mixing temperature. And here are my example data, and I just noticed that it's a little bit off screen. So in my example data, you can see that these are the initial temperatures. This is the final temperature for both the specimen and the water, and then the change in temperature is computed, the mass is measured, the specific heat capacities are given respectively, you have to look them up, and then the heat flow is computed. Of course, the heat flows should be the same because the heat flowing out of one object into the other must be the same. However, it's a measurement, so there's going to be some kind of measurement error which is calculated with this formula. This is the heat engine lab, and here are the objectives as well as some statements for the theory. And the theory actually goes on quite a bit. Some of these statements also go with the question about the procedures on the pre-lab. And then the procedures themselves are here, but because there are there's quite a few of different engines, the DC motor, the Stirling engine, the steam engine that is powered with this camping fuel SBID, respectively the electric powered steam engine. I would also refer you to the actual posted video on the heat engine lab. So there are some procedures here, but there are some procedures in that video as well. And then what you see highlighted here is as well for the pre-labs on procedures as well as what should be measured. For example, the masses are already determined because they're right here, because otherwise you would have to take the steam engine apart and would have to measure directly the mass of the rotating parts, and that's not recommended to take the heat engine apart. What you definitely have to measure is what's highlighted here as well as in bold, the total time that the heat engine runs, the stoppage time, and the frequency that the flywheel rotates. And then this would have to be calculated, the efficiency, the rotational energy, don't forget the square on the angular velocity, the moment of inertia, again don't forget the square on the radius. This is the lab for DC circuits, and here are the objectives, and here are some or all of the theory statements. And then these are the procedures on how to use the multimeter. as a voltmeter, as an ammeter, as an ohm meter. Here we go. And here are some or all of the procedures for the lab, as well as some as well as some example data, not data example, example data here for the resistors. Here are a few examples for the light bulbs. For example, to compute the time that batteries would last, it's take the rating of the battery, which is listed in amp hours on the battery, respectively in a footnote on this page, and divide by the measured current, and you get the number of hours that a battery would last. And that footnote I just mentioned is here on the same page. Here are quite a few important statements for the procedure. When I grade this lab, I pay attention to that these highlighted resistances, which are all measured or computed in a different way, are indeed yielding virtually the same numbers within measurement errors, of course. I also pay attention to that, for example, in a series circuit, that the voltages add up to the total and that the measured currents are the same throughout, because those two things are the nature of a series circuit. And then for a parallel circuit, it's also a certain way. It's just a little statement that the setups that I have here for a parallel circuit should be arranged like that, so that it will make it easy to measure individual currents. Okay. Oh yeah, and that these here, of course, are my example data. This is the lab on capacitance and the RC time constant. And here are the objectives. And here are some or all of the statements for the theory part. And here are some or all of the statements for the procedures. And here are some example data in the posted Excel sheet for charging a capacitor, for discharging a capacitor. The regression coefficient is really great on discharging here, and you see the nice curve. For charging the capacitor, the regression coefficient looks pretty good. However, look at the curve here, that only an approximation seems to be right, and this is where you have to adjust the voltage here to make the curve fit better. This one got better, the curve fitting got better, and I happen to know the result here. So that's why I was able to do it in 2 steps. Now the curve is perfectly, and now you can do something with the data, but that's also explained in the actual lab video. And that's it for this lab.